Section 5.1, page 5, the final page. We talked about the formula for the area under a curve, and we gave you the exact area being the limit of the summation of all the rectangles. This used that summation notation, but let's talk about summation notation just to better understand some of the fundamentals. If you're asked to add from I equals 1 to whatever total number, and you just have a constant, you're taking that constant like 5 plus 5 plus 5 plus 5 n times. So it turns out you're adding that same constant to itself n times, which is the definition of multiplication. A constant number is times the n value. Now, what if you had a coefficient and you were adding up some sort of number? So we don't really know what's happening here, but it turns out if you have a coefficient, or also thought of as a constant, you can kind of pull that out the same way we did with delta x. We always had the same width rectangles, so we said let's just add up all the different heights and then multiply by that constant width. Next, in terms of summation notation, if you have something you're doing to a variable and you're adding or subtracting that to something else that's happening to the variable, you could break it up into the summation of the first term, keeping whatever the sign was, the summation of the second term. So we're just going to break up sums and differences, kind of the way we did with derivatives and limits. Here's where it gets a little more helpful. You don't need to derive this. We're going to tell you that if you ever just keep adding each number to itself, 1 plus 2 plus 3 up to 17, 45, whatever n is, it's always going to find this format for the total. So for example, if this had been 50, we would have had 50 times 51 all over 2 and could do that math to find out the sum of each integer from 1 to say 50. If you ever have the integer squared, 1 squared, 2 squared, all the way up to whatever n is squared, it's always going to follow this format for the total. And if it's cubed, it's going to follow this format. So here's where those come into play. First, let's look at example 7. You're asked to write the sum in sigma notation, right? That capital Greek letter S is our sigma symbol, where we're going to have I equals, what do we start with, what do we end with, and what are we doing to those? So as I look at this particular pattern, generally we start with I equals 1 and we go up to some final number. So if we started with I equals 1, then 2, then 3, etc., then how does this compare to my fraction? Well, my first fraction had 1 in the numerator. It had 2 in the next numerator. It had 3 in the next numerator. So it looks like whatever I is, that's the numerator of my function. And because it stops at 19, then that would be my n value. So n is 19 and I starts at 1. But these denominators, what's going on with the denominators? Well, I went from 6 to 7 to 8. Okay, so they just keep getting bigger by 1 and we keep increasing integers by 1, but I didn't start with 1. So maybe you recognize you started with 6, but remember I equals 1. If I had written 6 plus I, that would have made this a 7. So we either needed to recognize it was 5 plus 1, or really I thought about it as 6 is what I have, but minus the 1 I was already using. So this would be my denominator. So now I could even test it out, right? I'm going to have 1 over 1 plus 5. Yeah, that's 1/6. Then I'm going to have 2 all over 2 plus 5. 2 7s, perfect. I'm going to have 3 over 3 plus 5, which is 3 8s. Yeah, so I know that this is my right answer. Now let's go ahead and find the value. Let's actually add them all up. And we may have to use some of the rules above. So the first thing I have is we're taking -2 to the I power. I need to go back and look at all my formulas. This is subscripts mean we're doing something to that variable, but none of them are to the I power. I have technically I to the 1, the 2, and the 3 power. So what happens here is I cannot use any of the rules above, but since n is just 4, this is pretty reasonable to go ahead and just find each term. So I'm going to start with I equals 0. It didn't start with 1, but it told me not to start with 1. And I'm going to put I, in this case, in the exponent. So I have negative 2 to the 0 power, which is 1. Next, I'm just always jumping by integers. So I'm going to have negative 2 to the 1 power, to the 2 power, and I'm going to stop at n equals 4. Anything to the 0 power is 1. A negative number by itself is just my negative 2. Negative 2 squared is negative 2 times negative 2. It's positive 2. But an odd exponent is going to give me 4 times negative 2 is negative 8. Times negative 2 is positive 16. So I'm going to add those to get negative 1. With this is, positive 3. Now I'm going to get negative 5 plus this is 11. So the math was reasonable on this problem. But let's look at the next one. K, it's not I, but that's okay because K is a variable that shows up in my summation problem, and it goes to 61. 61 is way too many to work out. I would never expect you to do that, even though maybe using Excel or your calculator could seem reasonable. So what's going to happen is I would look to see what formulas I have, and I do have a formula for I to the n power. No, I don't. What did I just say? It's squared, right? I think I said to the squared power, said it wrong. So where n is, well, n would be the 61, but that's actually if it's just I squared. I don't have I squared. I have something much more elaborate. So actually, I can't jump to that rule yet. What I want to do is I want to expand the thing that is squared, because I think of the formula for a perfect square, in my case, a minus b, maybe you normally think of it as a plus b. It's the first thing squared. So 2k squared is 4k squared. Always going to be plus the last thing squared. So 7 squared is 49. And then because this was a minus, I'm going to have a minus, and it's the first times the last. 2k times just 7, I'm thinking not negative 7, is 14. Wait, it's 14, isn't it? Oh, right, times 2. So that's where the 28 came from. So we also learned that when it comes to summations, we can break them up into separate notations if needed. So I'm going to have a summation of 4k squared, but I'm going to bring the constant or coefficient out front. I'm going to have a summation of just k, where I brought the negative 28 out front. And if it's just a constant, we're going to bring this here. So now, when I just have whatever my index is, k in this case, squared, I can take the index squared formula, and where n is, I'm going to swap out my n. So n was 61 for our problem, and we had pulled a 4 out front. I've got my minus 28 in front of k, and the formula for k was n times n plus 1 all over 2. So I put my 61 there, and we said if it's ever just a constant, it's a constant times how many times it's added to itself. So suddenly I'm really looking at, 61 times 62 times, this would be what, 123. So I can work this out to get each term and get a final answer. The last one, notice I'm asked for the sum of I equals 1 to, I don't have a number. So in that case, it's really impossible for me to try to add them up myself since I don't have that number for n. That just means my answer is going to have an n, just the same way all of our formulas had, n's in them. So I'm going to pull this 8 out front, and just summing up the index, we know is this formula, but since I have an 8 out front, I can cancel this 2 into the 8 4 times. And instead of writing 4 times n times that, I'm just going to write it so it's 4n. And I've now cleaned up my summation.